So now we are coming towards the end of this chapter, system of particles. We will complete oblique collision examples today, and then we will come to the last part of the chapter, which will involve variable mass systems. And then we'll put some time into discussing questions and doubts and all, because it's been a very lengthy chapter with a lot of different types of concepts and problem solving applications. So anyhow, let's begin. System of particles, session 10. So we were discussing about oblique collisions of two particles. So we saw that in general, in a situation of oblique collision of two bodies or two particles, the momentum conservation gives us two equations actually, because it's a two-dimensional vector relation. So if we have a body m1, so let's say going at velocity u1, and another body m2 or particle m2, which we can treat like a tiny sphere moving at velocity u2. So now one important thing is, when they come in contact, the collision impulse that acts, mutual impulse that acts between them, that always acts along what is called the line of impact. And the line of impact is going to be what? It's going to be the center to center line. Okay. So this is the center to center line, the line joining these two. That is the one which is normal to the plane of contact. So remember, the collision impulse is always normal. So the direction in which they apply force or impulse on each other on impact is going to be along this equal and opposite impulses. Hence, momentum is conserved for the system. Okay. So this is very important. The line joining the two centers of the particles, or you can treat the particles like spheres. Okay. Or if they are discs, like some of the examples we discussed last time. So that line is called the center to center line, or more appropriately, it is called the line of impact. So the line of impact is the line of action along which the collision impulse acts, or collision impulses, you can say. Impulse on 1 because of 2, and impulse on 2 because of 1. These two vectors, they act along that line. So in this diagram, you can see this is J12, impulse on 1 because of 2, and this is J21. Okay. Now, as a result of these impulses, their momentum will change. Okay. So for example, the first body here, it had a momentum in this direction. It had m1 u1 in this direction, and now it's experiencing an impulse in this sort of direction, let's say. Okay. So this is the impulse acting. So the final momentum it will have will be initial momentum plus impulse. No? It's like final momentum is equal to initial momentum plus impulse. So in this case, the final momentum m1 v1 after impact will become initial momentum m1 u1 plus impulse. So in the vector diagram that I'm trying to draw above here, you can see that if the impulse is like this, then the final momentum should be in some direction like this. So it should be initial momentum plus impulse. So it should be in this sort of direction. So the final velocity of this one, we can assume, will be in some sort of direction like this. And after impact, it will go off like this. So after impact, let's say it's after some time it's here, and it's having some velocity like this. Okay. Like that, if you follow for the second one, the initial momentum is in this sort of direction. Okay. M2, U2, and the impulse acting on it is in this sort of direction. Impulse on 2 because of 1 as a vector is this sort of direction. So the final momentum will be in this sort of direction. So M2, V2. So you can assume here that after this impact, probably it will go off in some direction like this. And this will be the final velocity. So this is what a typical oblique collision looks like. Of course, this type of collision is quite complicated to solve. The more simple version of this is what we were seeing in the last lecture, where the second body is at rest. So a moving body comes and collides obliquely with a stationary body. and then they diverge at some kind of angle. So here they are diverging at this kind of angle over here. Okay, so the momentum conservation equation always involves a two-dimensional vector relation. So when you break it up into components, it becomes two individual equations. Okay, and the choice of x and y axis is up to us, where we take the x axis and where we take the y axis, according to the convenience of the question. Okay, so one option is to take one of the initial velocities along the x axis. Another option is to take x axis along the line of impact. So that also, as we do more problems, you'll understand how this works. So everywhere we are using this concept that final momentum is equal to initial momentum plus the collision impulse. Okay, so that is what we have applied to get this final momentum and this final momentum, and at least get an idea about the direction. Okay, of course the value will come from calculation. So momentum conservation, okay, which is the standard thing in all collisions. Now momentum conservation becomes a vector relation that in general m1 u1 vector plus m2 u2 vector is equal to m1 v1 plus m2 v2. So as we were discussing, this vector relation or this vector equation is solved by component method, by component algebra. Okay, so to see some basic examples of the application of this concept, you can go through the 3 or 4 questions we did in the last lecture. So that's a good starting point for the basic applications. Okay, so let's now look at a little bit more advanced type of application of this. Okay, so we'll start looking into situations where coefficient of restitution is also involved. Okay, so now as we were discussing last time, how to understand the separation and approach velocity concept. So if the value of E, that is the coefficient of restitution, has to be used, okay, then in general what will happen is that we have to approach E, we have to express E as a ratio of separation to approach velocity. So now how do we calculate this separation velocity and how do we calculate this approach velocity? Let's understand that. Okay. So if you look at the situation just before impact, if these two bodies are here just before impact, and let's say that their velocities are something like this. This has a velocity like this of u1, and this has a velocity like this, let's say, of u2. It's clear, no, the diagram? It's clear, no? Above? Okay. So the thing is, which one? V separation. Okay. So that is separation and approach velocity. Relative velocity of separation and relative velocity of approach. Okay. So this is the what we call the separation velocity. That only I'm explaining below that how we'll calculate this. And this is the short form we are using for approach velocity. So this is a term that you have seen in kinematics before. Okay. Approach and separation velocity. Okay, so if this is the diagram just before they are coming in contact, just before contact. So the initial velocities are u1 and u2, and they are about to hit each other. Okay, so then to calculate the approach and separation velocity, what we have to do is we have to first understand what the components of u1 and u2 are along this line, which is the center to center line. So that is why this thing is very important, the line of impact. So if this is the line of impact, then the first thing we have to figure out from the diagram and the geometry of the given question is what are the angles made by the vectors u1 and u2 with respect to this line of impact. So suppose this angle is alpha and this angle here is beta. Okay, so in this diagram, can somebody tell me what will be the approach velocity? In terms of the given quantities, what will be the approach velocity?
Root cos beta minus u.
So it will be the component of the particle m1 towards m2 center. Adina, just once more think carefully, okay? Because see the direction of the second component. Yeah. So u1's component towards m2 center is how much? It is u1 cos alpha. So suppose the second particle had been stationary, then what the approach velocity would have been? It would have been simply u1 cos alpha. Got it? Now the second one is not stationary, no? It's also moving. So it also has an approach velocity. Okay, so suppose the first one was stationary and the second one was moving at u2, then how much the approach velocity? It is u2 cos beta. Again, the component towards this one center. So that's the cos component, u2 cos beta. Okay, now both the things are happening simultaneously and both are approaching each other. So it will be plus u2 cos beta. In this diagram, it will be u1 cos alpha plus u2. Yes, that's correct. Okay, so this would be the approach velocity in this diagram. And now similarly, if just after impact we know the velocities are v1 and v2, then by finding the components which are away from the center, going away from the center, we'll find out the separation velocity. And the ratio of this approach and separation velocity, that will become how much? That will become the coefficient of restitution. Or rather, ratio of separation to approach velocity, that will become the coefficient of restitution.
So before contact, both V's separation velocity and applied velocity, they lie on the line of impact.
Yes, that is the meaning of approach and separation velocity. Kinematics wise, if you have two particles which are moving at some velocities u1 and u2 like this, then at any point of time you want to find the approach velocity, you have to join the two particles and find their components towards each other. It's the relative velocity along the line of impact or along the line joining the two of them. Now in the case of the collision, you have to calculate this approach velocity at which instant? At the instant when the collision is just about to happen. So it will be not like something like this before the collision, but you'll have to see just when the impact is about to happen, what are the angles alpha, beta, and what are the values of u1 and u2, and accordingly you have to get. Understood, no?
Since separation velocity, it's away from each other.
Yes, separation velocity will similarly become away from each other. So to calculate separation velocity now, you have to redraw the diagram that what is happening just after impact. That is, the velocities are v1 and v2 in that case. So then you have to understand the components of v1 and v2, but along the line joining, but in which direction? Away from each other, not towards each other, but away from each other. Okay. So now you look at just after impact. So if the situation just after impact, due to the collision impulses, remember in the diagram we had seen that this one's velocity changes to some direction like this, let's say. and this one's velocity had changed to some direction like this, let's say. Okay, so again coming back to the line of impact. So let's just get this in a little bit more detail. Yeah. So center to center line. So this time you will see that they will have components which carry them away from each other's center instead of towards, because they're separating now. They're moving away. So let's say this angle is theta, suppose, and this angle is phi. So now in this diagram, just after impact, we can see that the separation velocity will become the sum of the components going away from each other. So it will become v1 cos theta plus v2, sorry, cos phi. So these kind of component concepts will have to be used if the value of coefficient of restitution is given in the question, and we have to incorporate that in our calculation. Okay. So that is the thing. How will we calculate theta and phi? So that all we'll have to do from some information given in the question, some geometrical information or something given like that in the question. Okay. So now, for example, so this part is clear. It's written down. Okay. So let's come back to one of the type of questions we had done in the previous class, but there we were not worried about coefficient of restitution. We were not worried about that. We were just solving the final velocities using momentum conservation, because a lot of information was given. Now let's see in that particular question how we'll make use of coefficient of restitution. So this was one of the first questions we had done as an example of oblique collisions. But as I said earlier in that example, we had not bothered about the coefficient of restitution. We had only bothered about the final velocities by using momentum conservation. So we had a question like this, where imagine you have two disks on a smooth horizontal surface which are identical, right? And one of them is moving and hits the second one, which is stationary, in an oblique manner. Okay. So this one is at rest initially. So A and B are identical disks, okay, let's say of mass maybe 1 kg each, okay, and make an oblique impact as shown. Now the given information in this question, I'll take the same information that we done that day. Okay, if their final velocities after impact, now these are disks which are on a smooth horizontal surface, so there's no friction and all that involved. So this diagram that we are seeing is like the top view of something happening on a smooth horizontal surface. So if their final velocities VA and VB are such that magnitude of VA is equal to magnitude of VB, okay, and VA is at 30 degrees with respect to V0, okay, and also given that magnitude of V0 is 10 meters per second. So basically particle A deflects by 30 degrees. Okay. Now we want to find, so that day we had already found the final velocities. So you may or may not refer to that. You can do this calculation freshly again. Okay. But now we want to find two new things. We want to find the collision impulse in magnitude. The collision impulse in kilogram meter per second or Newton seconds, how much that is. And we want to calculate the coefficient of restitution. How much is the coefficient of restitution for this particular collision? So these two things we want to do a calculation of over here. So now what we were asking is that how we will find these angles and all. So we'll see that the geometry of the problem will lead us to finding the angles. Now one of the angles is given to us, because it said that particle A is deflecting by 30 degrees. That means, if we compare the initial picture with the final picture, we can see that A was coming along that dotted line, and after impact it will go off at 30 degrees to that. Okay. And another information that is given to us is mod B is equal to mod BB. So hopefully that information will help us in such a way that not only we can find the magnitudes of these velocities, but we can also find the angle at which B goes away. So once we know that, we know both the angles. Okay. And through that we'll be able to calculate the separation velocity. Then we'll compare that with the initial picture before impact, and hopefully we'll be able to calculate the approach velocity also. So from that we'll calculate the coefficient of restitution. Okay. So that's how this question is going. So from this first diagram, first try to make the diagram of the impact. During the impact, what is the center to center line and all that, try to understand that. And then draw the diagram immediately after impact with this information and see how we can make use of this. Okay. So we will need to find out two things here so that we can get the coefficient of restitution and all that. We need to find out the magnitude of B and B, which is some common value, and we'll also need to find out what angle B is going off at. A is going off at 30 degrees, that's already given, but we need to find out that also. So what will that come from? That will come from momentum conservation. Okay, Adinath, I'll verify the answer. So once again in this, we will start by comparing the situation just before impact with the situation on impact, just about coming in contact, let's say. So when they come in contact, obviously the collision impulse will act along this center to center line. So this is our line of impact. And therefore, what we'll also understand is that after impact, this body will go off with a velocity along this line only, because it was initially at rest. Now, the body B was at rest. So because the collision impulse on it acts along this line, collision impulse acts along this line, and its initial momentum was 0. So it has to go off along that direction only. So this one has to go off along this line of impact. Whereas this one will go off with some velocity, say V1, which is at an angle of 30 degrees. This is VB at some unknown angle. As of now, that is okay. Remember, their masses are same. So J is equal to impulse on B because of A. That one is only equal to M into VB. Now compare that with the initial diagram. In the initial picture, A was moving along this line. With V0. Whereas B was at rest. Okay, so this is the situation. Okay. So you can see that in this diagram, this angle is again our unknown angle theta. So at least in terms of this unknown angle theta, we can see that the approach velocity is how much? It is V0 cos theta. Right? Okay. And in this diagram, what can we say about the separation velocity? Okay. It will be the component of VA going away from this. So the separation velocity, now let's say that is VA cos some alpha, where alpha will be this angle. So alpha we can see is basically 180 minus theta plus 30. Something like this, okay. Plus now VB is directly in that direction. Okay, so we need to, so to get these things, so now E will be equal to the ratio of separation to approach velocity. So to get this, we need to first find out how much is VA, how much is VB. They're same in magnitude, but how much is also theta. Only then we can calculate all these things. Okay. So where this will come from? This all will come from conservation of momentum. Now conservation of momentum is going to be very simple here, because the masses are equal and all this. Okay. So mv0 is going to be equal to mva plus mvb. Okay. Now for doing this conservation of momentum, let's take our x and y axis like this. Let's take x axis along. So we can write v naught as v naught I cap then, okay, and VA has the same magnitude as VB. So let's take that as V. So then we can write VA as V cos 30 I cap plus V sin 30 J cap. Okay. And likewise, we can take VB as same magnitude V but some unknown angle theta. So V cos theta I cap minus V sin theta J cap. So we'll substitute like this. Okay. So when we substitute these quantities in the conservation of momentum equation, so along the x-axis, the x component you can see of this equation will become that mv naught is equal to mv cos 30 plus mv cos theta. This is like the first equation that we get. And along the y-axis, we can see that the initial momentum was 0 because this was only moving along the x-axis. So the final momentum should also work out to be 0. And how it's working out to be 0? Because A has a positive y component and B has a negative y component. So they should cancel each other. So A's positive y component is how much? It is mv sin 30. Okay. So basically what we are saying is that after impact, A and B, they are moving like this now. This is having the magnitude V. This is also having the magnitude V. But with respect to our x-axis, this is at an angle 30 degrees, this is at an angle 60. Okay, so this is the diagram we are looking at. This is our x-axis, this is at y-axis after impact. So it's this equation. So this will become minus mv sin theta. So that's our second equation. So the second equation is the very simple one that will show us that theta is equal to how much? 30 degrees. Theta should be equal to 30 degrees. Okay. So from equation 2, we can see that sin theta is equal to sin 30, which means that theta is equal to 30 degrees. And then we'll substitute this in first equation. Okay. So from that we'll get 2v cos 30 is equal to v naught. So we'll get our value of v naught. So this will show us that v naught is how much? V is how much? V naught by root 3. So this will now show us that V is equal to V naught by root 3. And this is showing us that theta is equal to 30 degrees. So now once we got this, we'll be in a position to calculate the approach and separation velocity. So I'll come back to that, but first make sure you're okay with this part. Yeah, I think Adinath, E should be 1 by 3 if I'm not mistaken. Let me also verify. Okay, and V naught I had given as 10 meters per second. So V will become 10 by root 3 meters per second. So from this now we can also see the collision impulse. The collision impulse will be mvb in magnitude. So that is mv naught by root 3. Same I think we are taken as 1 kg, right? Yeah, m was 1 kg each and v naught was 10 meters per second. So let's use that value. Okay. So 1 kg into 10 by root 3 meters per second. So that is giving us our impulse, which will be 10 by root 3 Newton seconds or kilogram meters per second. So now the only thing remaining is we have to calculate the approach and separation velocity, so that from their ratio we can find out the coefficient of restitution. So we can directly substitute in these formulae also, okay, but we can just understand it this way better probably, that before impact, this is what is happening. This is having a velocity v naught, which with respect to the center to center line now, we know is at an angle of 30 degrees because theta is 30. So this angle is 30 degrees. Okay. So our approach velocity is becoming v naught cos theta, or 10 cos 30. So 5 root 3 meters per second. That is our approach velocity. Right. Now similarly, the separation velocity, once you implement this thing that this theta is 30 degrees, you will see it's a little more interesting actually than the above diagram. It's like this, that if this is the center to center line, then after impact, of course, this one is going with a velocity along this line only. Okay, VB, which is equal to V. Okay. But what about A? VA is at how much angle with respect to that? It is at an angle. So actually, I'll redraw this diagram. This angle is 30, so it should look smaller. So let me draw this diagram better. Okay. So this sphere is probably somewhere here. Sphere is somewhere here. So that the impact line is at a relatively small angle. So the impact line so with respect to our original x-axis, the line of impact is only at 30 degrees. So this angle is equal to 30 degrees, and the velocity of B is in this direction after impact. Now what about the velocity of A? It's actually in a direction like this. It's also equal to V in magnitude, but this angle is 30. Okay. So now if you look at A and B in that sense, you realize that with respect to this. It's like this. So this angle is how much? It is 60 degrees. It's theta plus 30, which is 60 degrees. Okay. So in this case, now what will be the separation velocity? It will be VB because it's going away, but minus VA cos 60. Understood now why minus sign comes in? Because that component is not away from B, it's towards B. So A is actually approaching B, but B is going away from A. Okay. So the resultant separation is happening at this rate. Okay. Now the magnitude of this VA and VBs are the same. Okay, so this will just become V into 1 minus cos 60. So that V was, remember, V naught by root 3, and cos 60 is half. So this becomes V naught by 2 root 3. Okay, so this becomes our separation velocity, or 5 by root 3. So V naught was 10. Okay. So let me just modify this a little. Okay. So our approach velocity is V naught root 3 by 2. Okay. And our separation velocity is equal to V naught by 2 root 3 or 5 by root 3. So now we can see that our coefficient of restitution is 1 by 3. So yes, Adinath, that answer was correct. So this is the coefficient of restitution. Okay, so every question will have some kind of combination of geometrical terms, which will give you this way to calculate separation and approach velocity, from which you can get coefficient of restitution. Okay, beta, so this is clear, no? This is clear. So we'll do a couple of more questions, okay, then you'll get more used to this. But all the concept of how this approach separation velocity came in terms of components and all that, this part is clear. Impulse, such impulse is equal to change in momentum now. Now look at the body B. It was at rest before the impact happened in this previous diagram. So its initial momentum was how much? 0. Okay. And now this impulse, this JBA, that is coming and giving it the momentum. No? So directly that impulse is equal to MB, the final momentum. Okay. And below we have calculated what that BB is. That is equal to the impulse acting on A. So that is why the momentum of A is changing from MV naught like this to MVA like this. It's changing because of that impulse acting. So if you look at the impulse momentum picture for the body A, it would be something like this. The body A's initial momentum was something like this. It was MV naught like this. Okay, this was the initial momentum of A. And then it experienced an impulse in this sort of direction. JE on B. So the final momentum is changing to this now. It's becoming MVA like this. Because final momentum is equal to initial momentum plus impulse. Okay. So final momentum is equal to initial momentum plus impulse. But in the case of B, the initial momentum is 0. So that's why the impulse is equal to the final momentum. So this is the impulse momentum for A. Okay. But similarly for the body B, initial momentum was 0. Okay. So that is why the impulse acting on B because of A, that only is equal to the final momentum of B. This relation. Okay. Okay, so now next let's look at the next level of question in this in terms of the complexity of the question. So why I'm saying next level, because this was a question where finding VA and VB was not difficult. We had to just do momentum conservation. There was enough information given in the question. But now we look at a question where finding VA and VB itself is more complicated because coefficient of restitution is given, and instead angles are not going to be given directly. Okay, so let's look at that kind of question. So now suppose we have this situation. Treat A like a disc or a sphere like this, and B like a larger body. Okay. And A is initially moving along this sort of direction, let's say. So this is the line along which A is moving. Now, one special parameter that we'll define over here is the distance of that line along which A is moving with respect to B's center. If you talked about this in the last lecture also, this is called the collision or the impact parameter. Okay, so that quantity is D. So now again, A and B are discs on a smooth horizontal surface. Okay. So this one is at rest initially, okay, which make an oblique collision. Now, given that mass of A is equal to 1 kilogram, mass of B is equal to 3 kilograms. Okay. Radius of A is equal to 2 millimeters. Radius of B is equal to 3 millimeters. Okay. And impact parameter D is equal to 4 millimeters. So D here is called the impact parameter. So impact parameter means it is the perpendicular distance of the line of action of A's initial velocity V0 with respect to B's center. So about line of impact, we'll understand one thing interesting, that if the collision parameter were to be 0, then we have a head-on collision, because that means the velocity is passing directly through the center of B. Okay, so that will satisfy the condition for head-on collision. Okay, if the impact parameter is greater than 0 but less than R1 plus R2 or RA plus RB in this case, then we have an oblique collision, which is the case over here. You can see that it is greater than 0, but at the same time it is less than the sum of the radii, because the sum of the radii is 5 millimeter. Then there is an oblique collision. And on the other hand, if D happens to be greater than RA plus RB, then there is no collision. There's no impact. They just miss. That would be a situation like this. This goes off without making contact. Okay. So all this information is given. Now we have to find. Now suppose E is also given to us, and E is equal to let's say E is 1/3. Okay. So we have to find velocity of A and velocity of B after impact. Okay. And the angle. So let's say we'll find mod VA and mod VB after impact, okay, and find the angle between these two vectors, that is BA and BB, how much angle they have. So this becomes like the maximum difficulty level question for oblique collisions, because the information given is very minimal. Okay, coefficient of restitution is given, impact parameter is given, so everything has to be worked out from this. So apart from momentum conservation, which will give us two equations because two components, okay, we'll also have to incorporate the coefficient of restitution or separation approach velocity concept, and we'll also have to incorporate geometrically this impact parameter and radii, what this means in terms of angle of contact or the line of action. Okay, so start by just making the diagram for the impact, and from that try to understand how the line of action will be inclined with respect to value of V naught. Also let's take, okay, so let's take V naught as maybe in this case 15 centimeters per second. So basically draw the two objects as they're coming in contact, and from that diagram with the values of impact parameter D and R1 and R2, you should be able to understand what angle the line of impact lies at with respect to this initial velocity V naught. Okay. So that's one critical thing. How long the charge lasts?
And the charge is in like 10 minutes. So yesterday I was attending lecture, this thing was running out of battery. So there was writing, I just put this thing here and I kept charging after I finished. By the end of the lecture it was full charge. So,
We also using one more.
so this is not a very I use one note on my laptop.
Yeah. So how much is this angle working on? See, this is a right angle triangle. This center to center distance will be how much? This is the video. And see the radii are given 2 and 3 millimeters. So D is 4. If you make this angle as theta or something, the angle between this center to center line and this dot vector, that is theta. This will make trigonometry to that angle. D is given 4 and R1, RA plus RB is given 5. So basically that information will give me the angle. Okay, so let's make use of. हाँ क्या हो रहा है? लेक्चर ले रहे हैं. हाँ और क्या? लेक्चर के लिए तो हूँ यहाँ पे. So now the initial velocity vector of this one is along this line. And this line's perpendicular distance only we already know from the center of the second one. So if this is the center to center line, this is going to be a line of impact. So we'll be very easily able to calculate this angle because we know that perpendicular distance. So that is the thing about this question, because we know this perpendicular distance d. So we can see over here now this distance will become r1 plus r2 from center to center, or ra plus rp. So sine theta is equal to d upon ra plus rp. That is over here 4 upon. So theta is coming out to be sine inverse of 4 by 5, which we know is 53 degrees. Okay. So this is the information that we are getting geometrically, right? And once we have this information geometrically, we can also see that approach velocity is how much? It is v naught cos theta. So it is 3 by 5 v naught. Because that center to center line is Ra plus Rb, no? Sum of the radii. Look at that triangle, the center triangle along this perpendicular. No? So two circles, when they come in contact, no? The center to center distance is sum of the radius. Okay. Now the same picture, how is looking after impact? Let's imagine that. Okay. So one thing that we know for certain is that this one will have a velocity, B will have a velocity which is along this line only, because it was at rest initially. So our VB will be along this line. Okay. Now VA is the one that we don't know what the direction will be. Okay, so let's just assume that VA is in some random direction like this. Some random direction like this over here. So this is our VA, such that it is making some angle, let's say alpha like this over here. So in this diagram, our separation velocity will become VB plus VA cos alpha, according to how I have taken it. Okay. Now we have to do momentum conservation. Okay. So for momentum conservation, since B's final velocity is in this direction, it will be easier if we take this as our x-axis, and therefore the perpendicular to this as our y-axis. Okay, we can take the other way also, but this will be more convenient. Okay, let's take this as our x-axis. So in this diagram also, this direction is our x-axis, and perpendicular to this diagram is our y-axis. So we have one angle known to us, which is coming from geometry. Okay, we are going to have to use the coefficient of restitution term. E is equal to 1/3. So separation velocity will become 1/3 of approach velocity. So we'll have this equation that VA cos alpha plus VB, whatever that is, will be 1/3 of V0 cos theta, or it will become V0 by 5, because V0 cos theta is this much. Okay, so this is like a second equation we have. The first equation was this, that sin theta was d upon r. So this. So in all, you will see how many unknowns we had: theta, alpha, VA, and VB. So 4 equations we require. 2 we are getting like this. So the other 2 we will get from where momentum conservation. Okay. So conservation of momentum. Now I'll show you what is the advantage of using x and y axis like this. The advantage is that when we do conservation of momentum like this, you can see that A's y component of momentum will be conserved. Does that make sense? Why should A's y component of momentum be conserved? Because the impulse acting on A is in which direction? Along the x-axis. Okay. So A's y component should remain conserved. Okay. So when we write the conservation of momentum, the x component of momentum before impact, how much it was? It was mass of A into V0 cos theta. That is, this body's momentum's component along the x-axis. After impact, how much it is? B is having a component along the x-axis, which is MB VB. Okay, and A is having along the negative x-axis, that is MA VA cos alpha. So this is our third equation. Right? And along the y-axis, it will be a very simple equation because B is not involved along the y-axis. Only A is involved. What is A's initial momentum? It is MA VA sin theta, and after impact also it is only A. It is MA VA. Sorry, MA V0 sin theta. And after impact, it is MA VA sin alpha. So this is our fourth equation. So out of all these equations, the simplest one is the fourth one because it gives us a direct result. So from equation 4, we can see that VA sin alpha, this component, is equal to V0 sin theta. So that is 4/5 V0. Okay. And V0 we had taken as how much? I think it was 15 centimeters per second, right? So this will become 12 centimeters per second. Okay. This will become 9 centimeters per second. Okay. Now, next thing we'll do is we will solve equation 3 and 2 together. Okay. So from equation 3. Okay. Now, what were the masses? MA was 1 kg, right? And MB was, I think, 3 kgs, was it, or 4 kgs? Let's check. 3 kgs. Okay. So from equation 3, what we'll get? MB, that is 3 VB minus MA, that is 1 into VA cos alpha. Cos alpha is an unknown quantity, is equal to MA, that is 1 into V naught cos theta. So V naught cos theta is how much? 9. So this is 9. Okay. So this is in kg centimeters per second. It's a momentum equation. And from equation 2, which is the approach and separation velocity one, we have this, that VB plus VA cos alpha is equal to how much? V naught by 5. So V naught by 5 is 7.5 centimeters per second. Yeah, approach is already given. Okay. So using that and the coefficient of restitution, we got this. This is from equation 2. But V naught is 15, so V naught by 5 will become, oh sorry, V naught by 5, my mistake, not V naught by 2. So yes. Yes, I will explain the conservation of momentum part once more. But so conservation of momentum, I'm just, this will be 3. So this will become 3 over here. Yeah. Now conservation of momentum is very simple. Here, what we are doing is we are doing this now, that MV naught or MAV naught is equal to MAVA plus MBVB. And then we are writing this in component form. So in component form, when we are writing like this, our V naught is like this. No? It is V naught cos theta I cap plus V naught sin theta j cap. Okay, our VA is like this. It is minus VA cos alpha I cap plus VA sin alpha. See the diagram and you will understand. Okay, because this is our x-axis. The line of impact, that only we have taken as our x-axis. Okay. And this is the tangent line. It's perpendicular to the line of impact. Now. That is our tangent line. That is our y-axis. Okay, so that's why we are getting this. So that's why VB. The reason for taking this is for convenience. The momentum conservation equation is easier to write. It's like this. Okay. So when we are writing this in component form, the individual components become like this. Okay, is this clear, Anshul?
Yes, sir.
Okay, good. So now you have to just solve these two. So you can see that, for example, if you just add them, you will get rid of VA cos alpha and you will get the value of VB. Okay. So if you add these two equations, you'll get 4 VB is equal to 12. So VB is coming out to be 3 centimeters per second. Okay. And put that back over here, so you'll get VA cos alpha. And now to get VA as a magnitude, you will have to take VA sin alpha and VA cos alpha's vector sum. So you'll see that interestingly, you are getting VA cos alpha as 0. So which means that VA is equal to VA sin alpha. So that means A just goes off along the y-axis. It does not have an x component, and B goes off. So that means the angle between VA and VB will be how much? 90 degrees, because alpha is 5. So that's just coincidental, but there could have been something else also. We are taking the masses different or coefficient of restitution different. Okay, so finally we'll get the value of VA then as 3. VA as 12. My mistake. Okay, and the angle between VA and VB will be 90 degrees. Okay. Okay, so now substituting this back in equation 2, for example, we can see that VA cos alpha is becoming 0. So that means now VA sin alpha was 12 and VA cos alpha is 0. That means VA itself is 12 and alpha is 90 degrees. Okay. So once we know that, now we know that VA as a vector quantity is 12 j cap and VB as a vector quantity is 3 I cap. So they are perpendicular vectors. So this is what's happening in this particular case. Yeah, so let's go over this. Okay, so the first thing that we did is the geometry part. Okay, that is in this first diagram. We understood the significance of using this thing, the impact parameter. Okay, so as they come in contact, at the time when they are just in contact, the center to center distance is 5 millimeters. Is the sum of the radii, and this perpendicular distance is 4. So that means the angle at which V0 is with respect to the line of impact, that angle is equal to sine inverse of 4 by 5. So we got that angle is 53. Okay. So once we know that angle is 53, we also know what the approach velocity is. It is V0 cos 53. So that's working out to be this much. Okay, 9 centimeters per second. Okay. Now the next thing is that we look at the picture after impact. Okay. So what's happening after impact is that V0 was V0 was given in the question. It was 15 centimeters per second in magnitude. Okay. V0 was given to us as 15 centimeters per second. Okay. Coefficient of restitution was 1 by 3, right? And masses were 1 kg and 4 kg. 3 kg. Okay. And this additional information that RA is 2 millimeters, RB is 3 millimeters, and the impact parameters 4 millimeters. So all this information is given. So we're making use of that. Now we look at the picture after impact. So obviously B was at rest before impact. So B will go off along the line of impact. So because B's final velocity is along the line of impact, that's why for convenience we have taken the line of impact as our x-axis. And the perpendicular line to that, the tangent line becomes our y-axis. Okay. So while B is having a velocity like this, A we can't assume initially is having a velocity along y-axis. We have to assume that it has both x and y components. And why I assume that it's having a negative x component is because normally speaking, unless the coefficient of restitution, because it's 1 by 3 here, but suppose it had been 2 by 3 or even 1, A being lighter, it would have recoiled. Would have gone backwards, like in a head-on collision. So that's why I assume that VA cos alpha is in the negative direction. Okay. Yeah, Adinat, to answer your question, if D is equal to RA plus RB, like when D is less than RA plus RB, it's oblique. If D is greater than it, clear misses. When D is exactly equal to RA plus RB, it is what we call a grazing situation. They just tangentially graze each other. Okay, so in an ideal situation, when they graze each other, there won't be any impulse that acts between them. So that's also kind of the situation where there is no impact, but it's like they touch each other and move apart, like that. So it's a bit ambiguous. That's why we do not include that part. Okay.
Okay, sir.
Yeah. So now coming back to this diagram, after impact, B's momentum is along the x-axis. A's momentum is like this, that it has a negative x component of mva cos alpha and a positive y component of mvb. Okay. So now from this diagram, we see that in terms of these values, VA, VB and all, what is the separation velocity? It is VB plus VA cos alpha. Okay. So this is how we are comparing the before and after picture. And from this comparison, we are getting another equation now, which is the coefficient of restitution equation. That separation velocity is equal to E times approach velocity. So we can see here that the equation that we are getting here is this, that our VA plus VB, VA cos alpha plus VB that is equal to 3 centimeters per second. So we're going to make use of this also. Okay. So to begin with, you can see how many unknowns we had. BA was unknown, BB is unknown. B doesn't have a y component. B is moving along the x-axis. Why it won't come? Because separation velocity. Separation velocity is along the center to center line. No, it's only the component of BA which is away from B's center. That only contributes. No? The other component does not contribute. Okay. So that's why that sign term doesn't come. Okay. So that gives us my second equation. The first equation was this one, the angle. Okay. Now we come to conservation of momentum. So conservation of momentum in vector form, it is this. Right? So when we write it in component form, it will be this. So this is giving me equation 3 and 4. Okay. And once you got the 4 equations, it's just about solving because we had 4 variables and 4 unknowns. Okay. So we solved these equations like this. From that, these are the results that we are getting. That VA is 12 in magnitude, VB is 3 in magnitude, alpha is 90 degrees, and theta we had already seen was 53. So finally, we can see the angle between VA and VB after impact is 90 degrees. Yeah.
Sir,
Yes.
sir, how can D be less than radius of B?
Sorry, how
How
can
can it be 0 at any point?
0 to tab hoga beta when it's a head-on impact. So that means that perpendicular distance is 0. No? That means the initial velocity vector V0 is passing through the center of the other one. What, no? This situation.
Okay.
See, this is the situation. So that's why we said it's a head-on case. No? This is at D equal to 0 case. Got it? No?
So, but like if it's acha, okay, okay.
But it's not the center to center distance. You understand? No? It's the line of
Yeah.
action of V0. No? So you extend that line of the vector V0 and drop a perpendicular from the center. That one is.
Yes, sir.
Okay, so all parts of this question are here. So this we are done with oblique collisions. We'll do some practice questions. Now next we'll look at an interesting question where there are multiple bodies, that is more than 2 bodies, which are simultaneously colliding in an oblique manner. So this is also very interesting question. So now we imagine we have three such bodies. with one of them moving like this initially and the other two stationary at rest. So A, B, and C are identical spheres, let's say. On a smooth horizontal surface. Okay. B and C are at rest and in contact, and A impacts them simultaneously, okay, with an impact velocity V naught, which has a line of action along the tangent at the contact point of B and C. So actually all this is clearly visible in the diagram. Okay. All this information is clearly visible in the diagram. Now what we are observing, or rather what the question is telling us, is that it is observed that A comes to rest on impact. Okay, that A simply stops on impact. Okay. So we have to find the velocity of B and C after impact. Okay. And we have to also calculate the coefficient of restitution for A and B's collision and A and C's collision, because there are two collisions happening simultaneously. Okay, so now remember they are identical spheres, so they have identical mass and identical radius. So try to figure out the geometry of their contact. When they come in contact, the center to center lines, how they will look. That will give you the direction in which the impulses are. Yes. A and B's line of impact will be at some angle theta above this line, this one will be below that line. Can you join the three centers? B and C are already in contact. What kind of a triangle you will get when you join the equivalent? Okay, so that tells you the angles. Yes, very good, Adinat, that's correct. Magnitude of VV and VC will be V naught by root 3, and the coefficient of restitution will be 2 by 3. Okay. So this is the answers we'll get. I'll work out the solution also, but if you got it, you can see that magnitude of VV will be equal to magnitude of VC, which will be V naught by root 3, and the coefficient of restitution for both will be 2 by 3 common value. Okay. Yeah, I mean, we'll get the answer in terms of V naught only. Okay. I'm not given a numerical value of V naught in this question, so we'll just get the answer in terms of V naught. say the contact looks something like this. Draw it exactly. Okay. So the center to center lines will be forming an equilateral triangle. In fact, of precise side length 2r, where r is the radius for each one. So now if we compare, once again we compare the before impact, during impact and after impact picture. Okay, so we'll see that before impact, this one had a velocity of v0 in this direction. And these two were at rest. Just a moment. So this angle is equal to this angle, equal to 30 degrees because it's an equilateral triangle. Okay. During impact, this applied an impulse B on A. I mean, impulse on B because of A, impulse on C because of A. So equal and opposite impulse on A because of C, equal and opposite impulse on A because of B. Okay. So the resultant of these two impulses will actually be backwards on A. So he will experience a net impulse which will be in this sort of direction backwards. Okay. So as a result of this, what is happening? A is stopping, whereas B is developing some velocity which will be in this direction itself, and C will develop a velocity which is in this direction. So these angles will have to be 30 degrees. Okay. So here the convenient thing to do would be to take this as our x-axis and take this as our y-axis. So we can see that before impact, the momentum of the system was mv0 I cap. After impact, it is becoming mvb cos 30 I cap plus sin 30 j cap plus mvc cos 30 I cap minus sin 30 j cap. So when we do the components along the x-axis, we can see conservation of momentum. Okay, so we can see that v0 is becoming vb plus vc cos 30, and when we do along the y-axis, we can see that 0 is equal to vb minus vc sin 30. Okay, so these are the only equations which are required. Rest, I mean, for finding va and vb, vb and vc. Okay, so given that this comes to rest, because that's known to us. Okay, so from equation 2, we can see that vb is equal to vc. So suppose that is v. So substitute in equation 1, and we can see that that common value of v will become v0 by root 3. Okay. So the magnitude of vb will be equal to the magnitude of vc, will be equal to v0 by root 3, and the angle between vb and vc will be 60 degrees. Okay. So vb and vc are at 60 degrees with respect to each other. Okay. Or you can say at 30 degrees with respect to v0 each. Okay. Now the coefficient of restitution. So in this diagram, you can see that whether you look at the pair AP or you look at the pair AC, what is the approach velocity for A towards B or for A towards C? It is v0 cos 30. So root 3 by 2 v0. And now in this diagram, you can see what is the separation velocity of B from A or of C from A. Both of them, they're having a separate of VC or VB, which is basically equal to this V. Okay. So our separation velocity is equal to V0 by root 3. Okay. So our coefficient of restitution now will become root 3 by 2 V0 divided by V naught by root 3. So our coefficient of restitution is, sorry, reverse of that, separation upon approach. So V naught by root 3 divided by root 3 by 2. So it should be 2 by 3. Sorry. Just put a bracket here. Okay, so hope this question is clear. All respects.
So in the y-axis, because VB and VC are equal in this case, so they cancel each other out.
Yes, exactly. VB's momentum has a positive y component and VC's momentum has a positive negative y component, and they have to cancel each other because A's velocity initially did not have a y component. Huh?
Yes.
Okay, so this more or less concludes collisions for us. Okay, we will look at one final revision type of problem for collisions, where we'll go back to the concepts of collision with rigid surface, collision of a particle with rigid surface. Okay. Like we had done at the starting of the last lecture. Okay. Because that's also something very common at JEE level, questions based on collision with rigid surface. So this one is something that at least initially looks like a bit of a tricky question. So we have like a combination of two inclined planes which are kind of in contact with each other. So this kind of situation. So it's like there is a corner between these two inclined planes. So this inclined plane is at 30 degrees, and the second inclined plane with respect to the horizontal, if we draw a line at the corner point over here, this angle is 60 degrees, suppose. And these are both smooth surfaces. These are both smooth inclined planes. So there's a sharp corner between these two inclined planes. At the intersection of two smooth inclined surfaces. Now what we do is we release a particle from this point here, okay, from rest. So it comes sliding down the first inclined plane, and we'll assume that it makes a perfectly inelastic collision at the corner point. It comes and impacts the second surface at that corner point in a perfectly inelastic collision. So if this height is h1 and this height is h2, we'll calculate by the time it comes here what is its velocity. So a particle P is released from the top point as shown, and here h1 is 20 meters, h2 is, let us say, 15 meters, g is equal to 10 meters per second square, okay, and makes a perfectly inelastic impact. At the corner. Find its velocity just after impact. And the final velocity v, which is shown in the diagram. When it reaches the bottom of the second inclined plane, what is the final velocity? Okay, so let's quickly work out this question. So inelastic impact, remember, means that there will be loss of kinetic energy at impact. So we can do conservation of energy from the initial point till before the impact. And then again, after the impact, till it reaches the bottommost point, we can again do conservation of energy because the surfaces are smooth. But we can't do conservation of energy right from the top to right at the bottom because in between there's an inelastic collision happening and there's loss of energy. That's the first thing. And second thing, remember that in a perfectly inelastic collision, what happens? The separation velocity is zero. So basically, whatever normal component, so it will go like that. It comes thick like this and goes exactly like that. It will not bounce off the corner. It will not separate from that surface. So separation velocity is zero because E is equal to zero. So the velocity immediately after impact will be in what direction? Parallel to the second surface. It will not have any perpendicular component. So that's the first thing. And second thing, remember the tangential component of momentum in an oblique collision is always conserved because the collision impulse is in which direction? The normal direction. So we have to use that concept. Okay. So try this out. Can you tell me how much will be the impact velocity at the corner? With how much velocity the particle will come and impact? And just tell me parametrically only as it's going from this point to the corner, how much velocity it will gain? Root 2 gh1. And that velocity will be at some kind of angle to this surface. So it has a tangential component and a normal component. So what will happen? The collision will absorb the normal component, whereas the tangential component will remain conserved. That's how you will find the velocity just after impact. And once you got the velocity just after impact, just conserve energy between this point and this point. So you get the final velocity. Yeah, mass is not given, but you can just assume some mass and then it will get eliminated, no? Because we are only finding the velocities, we are not finding the impulse and all that. So mass will ultimately not be required. Okay. So basically, you can think of it like a succession of three events. The first is sliding down the incline itself. Okay. Then the second is the impact, which is perfectly inelastic. So use the properties of that. Okay. And the third is the second part of the sliding action. Back to the previous question. Hmm? Yeah, I have to do that. No? Individual circle that. Achha. This. Actually, that one node is different now compared to. Okay. Achha, I can do one thing probably. I can do the stroke erase. Okay. So now that that is done. Okay. Okay. So the first part, as it's reaching here, the bottommost point, let's say. So as it's reaching this point, okay, its velocity vector will be along this kind of a line, okay, which is parallel to this surface. So what will this angle be? Can you tell me? I take this
30.
angle is, yeah.
30.
Yes, very good. That angle theta will be beta minus alpha, which over here by symmetry is 30. Okay, but in general, you can see that we're talking about this angle. This angle is the same as this one. Okay, and therefore it is beta minus alpha. Okay. So V naught is root 2 GH1, which in this case will work out to be 20 meters per second. And that theta is equal to 30 degrees. So now you can see on impact, what is the normal component of velocity or the approach velocity? That is V naught sine theta. But what is the tangential component? That is V naught cos theta. So that will become here how much? 10 root 3, correct? And this will be 10. Okay. Now the collision is perfectly inelastic. So E is equal to 0. So what should happen is that the particle should literally stick to the surface. It should not bounce. So after impact, how will the velocity look like? Just after impact. Just after impact, the velocity becomes like this. Should be tangential to this surface. Be along this surface. The normal direction, this is the tangential direction. So because E is 0, so what happens is that the separation velocity becomes 0. So the velocity after impact is purely the tangential component. That becomes our answer to the first part, that just after impact, the velocity is V naught cos theta or root 2 GH1 cos theta, which in this case is 10 root 3 meters per second. Right, this is clear? Okay, now let's say the velocity by the time you reach here is v2. So here to here you have again apply work energy also. So half mv2 square is equal to half mv1 square plus mgh2, because it's losing that much potential energy. So we'll get v2 as square root of v1 square plus 2gh2. So that is becoming 10 root 3's whole square, which is 300 plus what was this 15 now? So 2 into 10 into 15. So 150. So square root of 450, whatever that is. Okay. 300 plus 300, sorry. So square root of 600. So 10 root 6. So this is the final speed before. Okay. So this is another type of application of collision of particle. If E was not 0, then it would have bounced. Okay. So for example, if E is 0.5 or 1 or something, then we will calculate that after impact, there is a perpendicular component along with the tangential component, and the particle will go into what kind of motion? Projectile motion. From that corner, the particle will go into a projectile motion. So that would be another type of question, like the one we solved last time. Okay. So anyway, with this we finished collisions. So the major part of this chapter is done. Now in terms of theory, we'll discuss variable mass system, which is the last part remaining. But that's comparatively easy and small section. So the main thing is you have to concentrate on problem solving with momentum conservation and collisions, which is like 75% of this chapter in terms of number of questions and all that. So please do that this week. Okay, complete HC Verma at all costs and also work on questions from the module. Module questions, the first exercise, the answer key is not there. I'll be sending you the answer key by today or tomorrow separately, so you can verify that. Okay, so that's it for today's session, people. Wish you all the best. Have a nice day.
Thank you, sir. Bye, sir.
Bye.
Thank you.